Okay, so let's talk about thermochemistry today. And really what I'm going to address is a very simple concept that builds upon this idea of state function and the behavior of a state function, what a state function means. So the goal today, or the question, or whatever, however you want to pose it, is computing delta H, which is now H is the enthalpy of a reaction. So we subscript it with reaction, and we'll use this jargon or this nomenclature with a superscript here of 0 or O to signify that we're going to be doing this at 1 bar pressure, okay, 1 bar, 1 atmosphere, almost fairly close. And initially we'll start this at T is equal to 298.15 Kelvin. So that's our goal. For a particular chemical reaction, we want to compute something called delta H of reaction, and it has a superscript 0 to specify P is equal to 1 bar. Okay. And initially we'll start at 298.15 K. And so schematically, the chemical reaction that I'm going to pursue, I'm not going to pursue a specific one. We're going to have a very general expression as a chemical reaction, and that would be as follows. Okay, so this is our chemical reaction where we have components, chemical species A, B, C, and D. Our chemical species, so they can be either atoms, diatomics, molecules, whatever you want to call them. So these are our chemical species. Okay. And I'm going to create a set of our chemical species, and in that set, I'll label each chemical species I. Okay, so if I were doing a summation of species, for instance, so if I wanted to sum, I would sum over all species I, okay, that are in this set. Okay, so I would equal A, B, C, D. Okay, so that's just something that we will get to a little later. And then the nu sub i's, okay, again, for this first time, I'll say, this would be nu sub A, nu sub B, nu sub C, and nu sub D. And this is the Greek letter nu, Nu. Okay, these are the stoichiometric coefficients. That you all are familiar with. Okay, so these are the stoichiometric coefficients. They essentially give you some insight as to the molar, the relative molar amounts required for a particular reaction to take place. And this is a self-consistent set of numbers that allow for this reaction. And at the moment, we're only looking at asymmetric reactions in the sense that it's unidirectional. So what we have is a bat of A, for instance, or A independent of itself and B independent of itself. Somehow we take this state where we have A and B, okay, and then we get to a state where we have C and D. And so that's something to keep in mind here, is that the way this reaction is written, we're not assuming any reversibility, okay, so we can't go backwards. There's only one direction. And we're not really accounting for anything that is involving mixing. So at the moment, we're only interested in this thing called delta H of this reaction. And this delta H of the reaction takes as its initial state A and B separated, and its final state are C and D separated. Okay, so all we want to know is if I had some A and some B to begin with, what's the total enthalpy of that combination? They're not mixed yet, they're just there. And then finally, I have C and D in some form, and I want to know what the enthalpy of C and D is. And again, they're not mixed. Okay, so this is what this standard enthalpy of reaction is telling us. We would have to know something about mixing thermodynamics in order to get something a little bit more deep. Okay, so that's something to keep in mind as written. Now, the nu sub i's, one subtle thing that we should keep in mind is that nu sub I is greater than 0 if you have a product. Okay. So the stoichiometric coefficient, we're going to write this as an equation, or we're going to use, so this guy is more or less a schematic, okay? But when we do mathematical manipulations, we're going to have to treat the nu sub i's as numbers, and so in mathematical equations, nu sub i's can be positive or negative, okay, because of the nature of equations. So for products, in equations that we will encounter, nu sub I is greater than 0 because it's something that's produced, and nu sub I will be less than 0 for reactants. Okay. So that's something that we should keep in mind. All right, so let's begin our discussion as to how we want to do this, or how we will analyze this. Okay, I think, yeah, let's go with that. Okay, so let me rewrite the equation, expression that we're interested in now. Nu sub A plus nu sub B times B goes to nu sub C times D plus nu sub D times D, okay? And of course, the thing that we're interested in is delta H reaction at 298.15 Kelvin, okay? The way we'll do this is we're going to create a thermodynamic cycle. Okay, so delta H, or H is a state function. So we want delta H for the process where we go left to right in this equation. Okay, this representation schematically of this chemical reaction. But we're going to take another process. We're going to take another route to go from the left-hand side of the arrow to the right-hand side of the arrow. And we can do that because H is a state function. And since we're interested in delta H, it doesn't matter how we compute delta H, or what process we take, or what path we take. And the path that we're going to do or take is that, knowing that A, B, C, and D are made up of elemental forms, whether they be elements or some sort of stable representation or stable combination of elements, we're going to go through this path where we decompose each one of the chemical species that are involved in our chemical reaction, namely A, B, C, and D. Okay, so A could be water, A could be glucose, A could be a huge protein. Likewise for B, C, and D, they could be anything that is macromolecular or very small. Okay, what we're going to do is decompose these things into things that are very elemental or fundamental. They may not be necessarily elements, but they may be something that is stable. Okay, and so we're going to create a little reservoir, if you will. So I'm going to put a little reservoir here. Okay, and this is it's artificial. We can play these kinds of tricks in thermodynamics. So we're going to create a reservoir of elements. So we can treat these as elements. Okay, so we can perhaps have carbon or hydrogen in some form. And that form is elements in their most stable form. At pressure is equal to 1 bar and temperature equal to 298.15 K. Okay, so we haven't touched the temperature and pressure, okay, that we're interested in for the chemical reaction of interest. All we're doing is creating this reservoir of elements in their most stable form. And so an example is carbon, and this probably is covered in the text in more detail than I will cover, but for carbon, the most stable form at these conditions is graphite. So it's carbon solid. Okay, So in this reservoir of these elemental forms of our chemical species that are most stable at the conditions of pressure and temperature of interest, the elemental form that we would be having in this reservoir for carbon is graphite. Okay, so graphite is a sea solid. For oxygen, it would be O2. For hydrogen, it would be H2, et cetera, et cetera. Okay, so these are the most stable forms of the elements. So now what we're going to do is decompose A, B, C, and D, these species of interest, into their elemental forms, or these most stable forms. And the way we just do that is you draw an arrow. So we'll take A and decompose it into the elemental forms that it is comprised of. We'll do the same with B. We'll do the same. And then now what we'll do is we've decomposed A and B. Okay. Now what we're going to do is use those basic building blocks, those elemental forms, and then we're going to construct C and D. So now the arrows will go from here back up and here back up. Okay. So that's the alternative route, or the alternate route that we're going to use to compute the delta H for this reaction as we initially posed it via this other path to these elements, the most stable elemental forms. Okay. And each one of these arrows then is connected to something called the enthalpy of formation of the particular species A, B, C, and D. Okay. So this arrow would be corresponding to the enthalpy of formation, which we label delta H superscript 0, which means at 1 bar, subscript F, which means formation, and of course then we have to label A. That's for species A. Okay. This arrow, and of course at the moment I haven't said anything about the signs, but we will get to that. This guy is delta H of formation for B. Okay. And this guy will correspond to delta H formation of C. And this guy will be delta H formation of D. Okay. The other thing that we will agree upon is that H is equal to 0 for all of the things that are in this reservoir. Okay. So by universal agreement, this is sort of a, if you want to call it a calibration or some standardization. So chemists have agreed that whatever we consider as these most stable elemental forms, everything here has an enthalpy of 0. Remember how I said entropy is the only thermodynamic function that has an absolute 0. All of the other thermodynamic potentials, U, H, and we'll see a few more soon, they do not have an absolute 0 value. You have to have a reference point. And that reference point where you say, all right, we'll let this state be 0 is something that has to be agreed upon, or that's something that if you do an experiment or if you have a particular system of interest to you, you define the 0 of H, U, G, Gibbs, et cetera, et cetera. But that's something then that you would have to specify. So in this case, for enthalpies of reaction, everything in this box has H is equal to 0 by agreement. Okay, and so this is a standard. So all of these guys have enthalpy of 0, so this is by agreement or standardization. Okay, and so then an enthalpy of formation would just correspond to, in the case of, let's say, let's see, CO2. So if we wanted to make CO2, the gas form, right, we would have to start with carbon, which is in the form of graphite. Okay. Plus, we would have to have O2, O2, right, O2 in the gas phase. Okay. So this would correspond to something that would be an enthalpy of formation of CO2. If we wanted the enthalpy of formation of graphite, or O2, let's say, so, well, actually, let's do O2. O2 gas. Well, we would have to start with O2 gas. This is the most stable form that by agreement. Okay. And if we wanted to go to O2 gas, we would see that H here is equal to 0 and H here is equal to 0. And this is a very trivial case, but delta H is going to be equal to 0, delta H of formation of O2. Okay, so anything that has this elemental form has H equal to 0, so we don't have to worry about their enthalpies. Okay. It's sort of a theoretical construct, but that's fine. Okay, so with that being said, let me see. Let's do just an example for H2O. Okay, let me just show you a little bit more precisely. So for the formation of H2O liquid, okay, we can say we have 2H2 in the gas plus O2, gas goes to H2, okay. So the enthalpy of formation then for H2 gas is equal to 0. This has H is equal to 0. That's the most stable form. This guy has H equal to 0. Okay. So for the enthalpy of formation of H2O, in this case, is going to be equal to the enthalpy of H2O at 1 bar pressure minus the enthalpy of H2 at 1 bar pressure minus the enthalpy of O2 at 1 bar pressure. And you see here that because we've defined these guys as 0, that enthalpy of formation is essentially the enthalpy of H2O. Okay. So that's the importance of having this reservoir of most stable elements that have all been defined to have H equal to 0. Okay, so let's see how this works. Back to our chemical reaction. Let's see, where did it go? Right here with A, B, C, and D. Okay. So our delta H then for reaction, okay, is going to be, so this is delta H at 290, let me write this at 298. So first we're going to have a contribution from this guy, right? So we're going to take A, we're going to form A, but we're going to go in the reverse direction, okay, to the elements. And so that contribution for that step is going to be nu sub A, okay, times delta H formation of A. Okay, then we're going to have this guy. Okay, we're going to have nu sub B times delta H of formation of B. Okay. Plus we'll have nu sub C times delta H formation of C plus nu sub D times delta H formation of D. Okay, so those are the contributions that we would have for delta H. Okay. Now I haven't said anything about positive, negative signs yet, and you'll see in a moment how this all works out. Okay. But does everyone see how this delta H is being summed up? Is there any issue with that? Is that clear? Or are there issues or? Okay, so it's just computing delta H's for a particular process. And in this case, instead of going from left to right, what we're doing is we're going to go around. Okay, and we're going to go around through this little reservoir of elements. Okay, that's all we've done here. Now, we know that nu sub C and nu sub D, because they're products, are going to be positive, and we know that nu sub A and nu sub b, because their reactants are going to be negative. Okay, so it turns out then that delta H reaction at 298.15 Kelvin will be nu sub C times delta H formation of C plus nu sub D delta H formation of D minus whatever we have as nu sub A. So we have to use the absolute values, okay, times delta H formation of A minus nu sub B times delta H formation of B. And all I've done here is removed. So in this expression, see, this was an equation, a mathematical equation. And because we defined our stoichiometric coefficients to have positive and negative signs, they would automatically obey the fact that the contributions from the delta H formation for A and B would have to be negative, okay? Because we're not forming them, we're decomposing them. So their delta H of formation would have to be negative. Okay? So delta H of formation has a sign. There's a directionality to it. The thing that you're forming is always on the right. So you're going from the elemental forms to whatever it is you're forming. In the case of decomposing something, you would be going in the opposite direction. And so delta H of formation would have to be taken as a negative. But that's okay, because the stoichiometric coefficients in a chemical reaction take care of the sign. And that's why we can use delta H of formation without having to worry about the sign of delta H of formation, because the stoichiometric coefficients take care of that. So in this expression, the stoichiometric coefficients would have just given us the signs. What I've done in this expression is just to use the absolute values of the negative stoichiometric coefficients, and I've introduced the signs myself. So this may be something that is more familiar to you all, but I've tried to do it both ways so that it's something that you can see and you can compare the two expressions, okay? And these two are equivalent because of the fact that we've defined the stoichiometric coefficients to have positive and negative values, whether they're a product or a reactant, okay? So these two expressions in the box then allow us to write delta H of reaction very generally, okay, as a sum over I, where I now is the set of reactants and products. So I is an element of this set of products and reactants. Okay, so I have a set that includes products and reactants. That's what's in the curly bracket. And what this means is I is going to be an element of that set. And I'm going to sum over all the I's, which means I'm going to sum over all products and reactants this product. And it's very simple. Nu sub I, as you see in the boxed expressions, times the delta H of formation of I. That's what we see in those two boxes. And the nu sub i's take care of the signs, as long as you're careful to understand that, again, reactants have negative, products have positive. So this is delta H of reaction at 298.15 K. So all you need to be given are the enthalpies of formation. And once you have the enthalpies of formation, and of course you would be given a balanced chemical reaction, you can compute delta H of reaction at that temperature of interest. In this case, the enthalpies of formation, standard enthalpies of formation, are at 298.15 K and pressure of 1 bar. So this is it. That's what enthalpies of reaction are. And so perhaps you've been measuring these in your first year Gen Chem class or what have you, but this is the formalism that is used to theoretically understand delta H of reaction. So any questions? And so this is the connection with enthalpies of formation of particular molecules. So all molecules have some sort of enthalpy of formation, whether it's measured directly or indirectly, but you can always find delta H of formation for a particular species. And these are tabulated. So delta H of formation of I are tabulated. Okay. Or they can be deduced, from tabulated values. Okay, so you don't have to memorize them. You're given those values. Okay, any questions so far? I'm going to move on. So from my point of view, these types of calculations, really the way I'll do it is just give you some delta H of formation for some things, and you can compute delta H of reaction at standard conditions. So these are standard conditions, 1 bar, 298.15 K. I'm not going to get too overly complicated when it comes to thermochemistry. I think there's other important things to conceptually consider in this course, and you've probably already done this kind of stuff in lab and probably Gen Chem. Okay, one final thing about thermochemistry that I want to address. So any questions? I'll pause here. Okay. So the final thing I want to address with thermochemistry is what about delta H reaction at T not equal to, okay, so really what this is just delta H reaction at T. Okay, and so we carry along the superscript 0. Remember, the superscript 0 only indicates P is equal to 1 bar. Okay, so the early part of this lecture was for 1 bar, 298.15 K. Now the question is, what about P equal to 1 bar, but some other temperature, T not equal to 298.15 K. Okay, and that's what we'll address now. And again, we can use the same concept for H being a state function. Okay, and this is the path that we will use. Okay, so we have our reaction nu sub A times A plus nu sub B times B goes to nu sub C plus nu sub D times D. Okay, we already computed this. Okay, in the above discussion. Okay, so this is a known. We'll consider this now known. Okay, you can use tabulated values of enthalpies of formation, so you know how to get that at 298.15 K. The question now is, what is nu sub AA plus nu sub BB goes to nu sub CC plus nu sub DD. And now we have delta H reaction at T. And T is some other temperature that is not equal to 298.15 K. This is rather simple because of the fact that H is a state function. Okay, and what we'll do now, again, find an alternate route. That's very simple. What we'll do is we'll take A from whatever temperature it is at this upper state that I've written, delta H reaction superscript 0 T. We're just going to bring A from whatever T is to 298.15 K. We're going to bring B from whatever T is to 298.15 K. We're going to do the reaction at 298.15 K, for which we know delta H, okay, based on the earlier part of this lecture. And then all we're going to do is take C from 298.15 back to whatever the temperature is. And then we're going to take D back to whatever the temperature is that we're interested in. And so each one of those arrows, right, just as all the arrows so far in this lecture have a delta H. So this is delta H for, let's say, stage 1 or process 1. This is delta H for process 2. This is delta H process 3. And this is delta H for process 4. And of course, these processes 1, 2, 3, 4 is just arbitrary. I can call it whatever I want. right? It's just a nomenclature. The concept here is the important part, which is that we're doing this alternate path because h is a state function, and we are totally free to do that. Okay, and now it's just a matter. So what you see here is that this delta H at the higher temperature is just the sum of the arrows plus the delta H at 298.15 K. Okay, and so we can write that this way before we fill in everything. Delta H, again, that superscript 0 means 1 bar pressure at whatever T is going to be delta H1 plus delta H2 plus delta H reaction at 298 plus delta H3 plus delta H4. So that's it. I mean, so simple, right? And that's because H is a state function. All right. So now it's just a matter of getting the delta H's for the individual processes, and those also are things you know. Okay, and there's nothing difficult here. Since this is at constant pressure, right? Because in both at both temperatures we have a superscript 0 signifying P equal 1 bar. We know that delta H is equal to Q sub P. Okay, so at constant pressure, we know Q sub P is equal to delta H for any kind of reaction. Okay, and we know then that dq, oops, right, that's fine. dqp is equal to dh. Right? So that's something that we covered as a fundamental idea in this class a long time ago. So that allows us to compute all of these delta h's. Okay, so let's do that. And now I won't get too much into the details of this. Let me just reiterate that dqp then is equal to Cp of T dt. Remember that, and that's going to equal dH. Okay. And so then delta H is equal to the integral of dqp, and that's just equal to the integral from T1 to T2 of Cp of T dt. Okay, any questions? All right. All right, so this is the expression that we'll use. And let's do it. So delta H1. Okay, we go back to this equation here, right? We have to get delta H1, 2, 3, and 4. Delta H reaction 298.15 is, again, what we already covered at the earlier part of this discussion. So delta H1 corresponds to species A going from a temperature T to a temperature 298.15 Kelvin. Okay, and we know that there's nu sub A. If we had to do this on a per mole basis, we have nu sub A, moles of A. So delta H1, using this expression, delta H1 is going to be the integral from T1 equal to T, whatever that is, to 298.15 Kelvin. So that's our final temperature of nu sub A times the Cp molar of A. And the way we'll write Cp molar of A is with a little bar up at the top of T times dt. Okay, everyone follow that? So now Cp A is equal to the molar heat capacity at constant pressure for species A, and likewise for all the other species. So delta H1 is just that. Delta H2, which is now bringing B from temperature T to 298.15 Kelvin, is going to be the same, 298. But now we'll have everything with B. And we retain this temperature dependence of the heat capacities. Okay, and so now we have these two, and now we're going to compute delta H3 and delta H4, which is taking C from 298.15 to whatever T is, and likewise for D. And that should be fairly simple. Delta H123 is equal to, now we're going to start at 298.15. We're going to go to T, and this is going to be C, the molar heat capacity of C as a function of T dt. And we'll do the same from 298.15 Kelvin to T of nu sub D dt. Okay, so those are our delta, 4 delta H's, 1, 2, 3, 4. And of course, we know delta H of reaction at 298.15 K. So any questions on that? Any questions at all? Okay, so at the end of the day then, there you have it. You don't really have to make anything more complicated. If you want the enthalpy of reaction at another temperature, you have the enthalpy of reaction at 298.15 Kelvin. And all you have to do then is compute the enthalpies of reaction. We're taking all of the species involved in this transformation at temperature T between 298.15 K and whatever temperature is of interest. That is that simple. And so these are the expressions. I know the textbook probably uses this delta CP and all of that, but you know, you can choose to think about it that way, but the most simple thing is this, and as I've said, that's all you really have to understand. If this heat capacity, CP molar, are all constant or weakly dependent on temperature over the temperature range of interest, then you can just take Cp of T to be a constant. They all come out of the integral, and you can do the integration very simply. And so as an example, if Cpa molar of T is weakly temperature dependent, then delta H1 is equal to Cp of A molar times nu sub A, because nu sub A is just a constant, times the integral from T to 298.15 Kelvin of dt. But the integral of dt between the two things is just 298.15 Kelvin minus T. And so that would be delta H1 if Cp is weakly temperature dependent, and you can assume that it's constant. Okay, and likewise for delta H1, 2, 3, 4 for species BCD and whatever species you have. Okay, so any questions? I think that's rather simplistic.
I had a quick question.
Sure.
Does the sign convention for nu still hold in these set of equations, or no?
Oh, great question. No. So yeah, that's a good question. So you would use the absolute in this case, because the delta H's will take care of the limits of the integration will take care of the H. All you need to know here, since Cp is molar, all you need to know is what the molar, how many moles of a particular species are going to be involved. So you would use the magnitudes of the stoichiometric coefficients. That's a great question. That's a great question. Okay, so are we clear on that?
Yeah.
Very good question. I'm glad you brought it up. I appreciate it. You are right. You are right. Okay, so so here I would have to use this and this, right? Is everyone clear on that? That was a great question. My apologies for the oversight.
Clear.
Okay, great. Cool. So that's it. I'm gonna make life simple. That's thermochemistry in a nutshell. How to compute it at 298 and 1 bar, and then how to compute it at a different temperature. These are the two basic tools that you'll need over and over, and then anything else is just icing on the cake and further nuance. So I'm not going to worry about it. Okay, I'm going to move on then if there are no other questions. And thanks, Michael. I think you pointed out the stoichiometric coefficient issue. Okay, great. Let's get on with some other things now. So last class, I introduced the fundamental equation. So the next set of points or concepts that I'm going to address deal with spontaneous processes, or how to, let me just write it down. Spontaneity and stability. Okay, so that's the overarching theme now for the next few lectures. Okay, so how are we going to sort of have some intuition about whether a process is spontaneous? So just as with a chemical reaction, we discussed earlier on, is that chemical transformation or is that process going to be spontaneous? And if it is spontaneous, how do we characterize it? How do we quantify? How do we have some quantification for that spontaneity? And then how will we know once that process is over, what happens when we have a stable system at equilibrium? Okay, so we want criteria now, some formulation or some formalism that allows us to understand spontaneous processes and stability of a system. So criteria for spontaneity and stability. And we already saw one criteria for spontaneity or irreversibility, and that was that delta S in an isolated system is greater than 0. Okay, so that's what we're after here. Okay, so for an isolated system, we saw that if we have a spontaneous process, delta S is our guiding criterion, or ds delta S, either one, ds and delta S would be greater than 0. Okay, so we want to see how we can build that up for some other types of things, okay? And this will be very insightful. And I think this is, again, one of these cool conceptual parts of the course. So let's start with this idea. Okay, so this is the overarching theme for the next few lectures, overarching theme for next few lectures. So this, the criteria, and then how we apply them. Okay, so we saw in our discussion of entropy that ds is equal to dq reversible over t, and this t is something that we can take as the t of the system, or we can take this as dq reversible t surroundings. So remember when we had our engine, remember in the Carnot cycle we had our engine, and this reservoir was at T hot, and the way we had set up the system was that we have Q hot coming into the engine, which is our system, at a temperature T hot. So that means that the engine is also at T hot. That part of the system is running at T hot. Okay, so the system temperature and the surrounding temperature both have to be at T hot. Okay, whatever that is. Okay, that's why I've written this as I've written it here. And then the same when we have Q cold being dumped to T cold, that part of the engine, whatever that part may be, has to be at T cold. And this is obvious when you look at the PV diagram, because the isothermal steps, right? So this happened at T hot, and this happened at T cold, and they were isothermal. And this cycle represents the system, the engine, the gas, the ideal gas in the system. And so the system is at T hot and the system is at T cold during those isothermal steps. And T hot and T cold are also the temperatures of the reservoirs. Okay, so that's why I was able to write ds is equal to these two things, where I use T system on the bottom in one case and T surroundings in the on the denominator in the other case. Okay. The other thing I want to point out is that dq irreversible is less than dq reversible. And this was what led us to, or we use for Clausius inequality. Okay, that was what allowed us to write that this thing dq over t is less than or equal to 0 over a cycle. Okay, right? So what we can say here is then that if we have something that is ds, which is equal to dq reversible over t, right? That's going to be less than dq irreversible over t. Okay. And here we can let this be t surroundings, which is the same as t system. Okay. Does everyone follow this expression? This comes from the fact that dq irreversible is less than, oh, do I have the wrong sign there? I do, don't I? This should be this way. So dq irreversible over t surroundings is less than dq reversible over t surroundings. And this guy is equal to ds, right? So that's what this ds is equal to this guy is. If that confuses you, then what I'll do is just write this guy as ds. Everyone clear on that or no?
Clear.
Okay, so what that allows me to do then is to write dq irreversible is less than t surroundings ds. So all I've done here is multiply by t surroundings on both sides, but I know that dq reversible over t surroundings is just ds. Okay. So what this is saying is ds is greater than dq irreversible over t surroundings. So if I multiply by t surroundings on both sides, I get dq irreversible is less than t surroundings times ds. Okay. And I can generalize this. So dq irreversible, okay, I use the inequality, but I know that dq reversible is equal to t surroundings ds. Okay, so therefore I can write in general dq is less than or equal to t surroundings times ds. So this is the general way I can write this. That less than or equal to, it takes into account both reversible and irreversible conditions. Okay, one final thing. Once I have this guy, I can go back to the fundamental equation. Remember, that was just du is equal to dq plus dw. And so du is equal to dq. Let me isolate dq. What I'm going to do is write dq is equal to du minus dw. Okay. But I know dq from this guy, that's going to be less than or equal to t surroundings times ds. Okay. So what I have then is this guy left over. So du plus p external dv is less than or equal to t surroundings times ds. Now I bring everything over. What I get is du plus p external dv minus t surroundings ds is less than or equal to 0. Okay, that's what this allows me to do. Okay, so p external is this pressure of the surroundings. You can say we know that that's we could have used p surroundings here, right? And we have p surroundings as well in this expression. So let's just think about this. What has this given us? Okay, well, if we have an isolated system, and then I'm done, we know that dv is equal to 0. We have something that has rigid boundaries. And we know that in an isolated system, energy is conserved. There is no change in energy. So du is 0, okay, for an isolated system. So what that leaves us with is minus T surroundings, ds is less than or equal to 0. Okay. And then if we multiply by negative T surroundings, both sides, what happens is we get ds is greater than or equal to 0. Wow. So we've come at a result here for an isolated system that we've already seen before, but now it's coming from a very compact expression right here. Okay. And what this means is that ds is going to be greater than 0 in an isolated system for a spontaneous process. And then once we have equilibrium and the system has stabilized, or we have a system that is stable, ds will be 0. That's the take home. And it all comes from this guy. And we're going to see a lot more that arises from this equation, which is very, very important as we continue next week. All right, any questions? I'm going to end the lecture there. And any questions at all? Okay, I'll recap that aspect and we'll move on. And now we'll get to Gibbs and other things, Helmholtz, that will naturally arise from this expression. And you'll see why they're useful. Okay, have a great weekend. I wish you all a safe weekend. And thank you for your attention and participation.